Hello. I hope everyone can see me. Anybody there? Anybody around? Hello, Logan. Nice to see you again. If you are indeed the same Logan. The aliens are coming. Watch out. Yes. Hello again. Nice to see everyone. We're going to do what we usually do. Hey, Zane. And wait maybe like 60 seconds, 90 seconds, something like that, to see if anybody else shows up. What does Arrhenius mean? I believe the word is just the person who came up with the equation. It's the equation that links rate and temperature, but I think it was the person. But if somebody wants to Google that specifically, then go for it. I mean, like, it could be confusing. Hopefully not. The aim of these is for me to explain things properly so that they're not confusing. So, you know, I mean, like, it means that you won't have gone over it before, but it doesn't mean you can't understand it now. Hello, Fatima. Is this KP and KC? This is an equilibrium. So KP and KC are equilibrium. This is rate. Oh, good for you, Aisha. This is excellent timing for you. Hopefully it will help. Okay, all right. I think let's give it the amount of time it takes me to figure out how to share the presentation with you guys. I will be explaining what the topic is, Aisha. Oh, there's two Aishas. I'm going to call you guys Aisha A and Aisha J to sort of make things less confusing. Okay. Let us get started. I think that should be everything shown. Okay, wicked. So we're going to be doing rate in the Arrhenius equation. And I do want to sort of like give you guys an idea of what exactly we're going to cover, but that's going to be in a second, because first I need to introduce myself and SnapRevise and sort of all of those things. So don't worry, I will give you a gist, but like just in about 60 seconds. So you only have to wait that long. If you've not seen me before, I am Georgia. I sort of am the head of chemistry here at SnapRevise. So I'm doing all of the chemistry web classes. I have a master's in sort of natural sciences, specializing in chemistry, and I've been teaching chemistry for about 6 years. So it's been a while. Hello, Princess Rositosa. I like your name. I too wish I was some kind of princess, but it would probably be a princess of science or something nerdy like that. Okay. So the point of the web classes, they are to be a recap, key points, not every tiny detail that you'll ever need to know. You guys as A-level students should be taking responsibility for making sure you know all of your tiny details. Of course, you will do them in school as well, but like definitely be checking those from your spec points, which I will be showing you in a bit. Did I just start? Yes, I just started. So don't worry, you haven't missed anything important apart from my name, which is Georgia. We'll also be doing quite a few exam questions because those are super important. Your revision should really be geared towards those. And just a note, this is free right now. Hurrah, free stuff. But it won't be forever. There will be, most of the web classes will be part of our sort of new launch for our ultimate package on the 16th of October. But we will have a few free ones just in case, like, we do get that, like, not everybody can afford to pay for things. So there will be a few free ones, but most of them will be part of the wonderful package. And I will tell you more about that later because we want to learn more rather than do sort of, what are we doing? Giveaways. So are all the live free? So the ones you're watching now are free, but they won't, not all of them will be free after the 16th of October. But good news is that sort of the web classes, we have like a giveaway. So if you follow us on Insta and share a picture of the web class on your story and tag us in it, you might get a free account. So that's super, super useful. After October 16th, Aisha, they're not all free. Some of them will be free, but not all of them after October 16th. And we also have a coupon at the end for discount. So hopefully that helps some people out as well. Do the winners of the free account also get the SnapRevise 2.0 for free? So anybody with an account now or gets an account today or before the 16th will automatically be upgraded to the basic package. So yes, but not like everything. When are you starting physics? I cannot tell you that, but my colleague will let me know when they know, and I'll let you guys know as soon as we know about that. Okay, so you wanted to know objectives, what we're actually going to be doing this one. So we're going to be doing, last time we looked at time concentration graphs, which are distinct from rate concentration graphs. So we're going to be looking at rate concentration graphs and figuring out order of reaction from those and the rate constant. The next thing we're going to be doing is looking at the effect of temperature on rate. So that's our Arrhenius equation. And then we're going to be looking at rate determining step and how to predict it from experimental data. So we're not going to be covering iodine clock reactions because that's really specific to some exam boards. Sorry, you can ask how long it's going to be. It's not rude. So it should be about an hour, but the questions often run to about an hour and make it run to about an hour and 15. So I'm gonna say hour and 15 tops because I'm going to be more careful today about getting things to end quickly. But yes. So, and hello, Taiwo. Probably pronouncing that wrong. Guys, if I ever pronounce your name wrong, I really do want to learn. So please do give me a little pronunciation guide in the comment so that I can say your name properly. I know how annoying it is when people can't say your name, so do that. Right. So we're going to get, wicked, I got it right. That's exciting. Cool. All right, so what I'm going to do is we're going to recap all the things that we should definitely already know, either because you came to this class on Thursday and we covered the basics of the rate equation, or from school or from GCSE. So I'm just going to get my pen out and we're going to talk about what we should know already. So a quick note on when I ask sort of questions, the best way for you to learn is to be engaging with me. So just listening is actually a really terrible way for your brain to take in information because it doesn't think it's important when it's just listening. It thinks it's important information and should remember it when you're sort of doing things with it. So when I ask a question, try to write an answer in the comments, or if you're too nervous or you don't know, still be thinking about it because otherwise you probably are not going to remember it. So let's get started. On that note, can someone tell me what the rate equation is? What is the rate equation? It shows how the rate constant varies with temperature and activation energy. Almost. So what you're thinking of, Jaisal, is the Arrhenius equation. The basic rate equation is slightly different. So yes, Leonide, you are correct. It is a mathematical equation that relates rate of reaction to concentration, but I want to know what it is exactly. And Zoysia has wonderfully let us know. So the rate equation is rate is equal to K, which is the rate constant. So that gives you a little bit of a clue as to the next one. And it's the rate constant times the concentration of our reactants. And then sometimes you have a power here, and that power tells us the order of reaction, but we'll go into more detail with that over there. So just a quick reminder, any square brackets? Can anyone tell me what do square brackets always mean in chemistry? Concentration. Yes, thank you, Zane, Fatima, Deca, rated mega. What an interesting name. Yeah, square brackets mean concentration. So keep that in mind. Yes, okay, so I mentioned the rate constant here. So we know it's K because I've labeled it. So it's K here. So what is K? I'm going to sort of give you a clue and say K tells us about the relationship between something and something. And if you're looking at the rate equation, you can probably tell me what it shows the relationship between. Anyone want to take a stab at telling me what K is? Sammy, I don't know what that word is, or if it's a sentence or some other kind of mystical word thing. Rate constant. So anybody? I'm going to give you like another 10 seconds. Oh, I didn't see Leonide. Proportionality constant between the reaction rate and the concentration of reactants that appears in the rate equation. Yeah, beautiful. I word it something like very slightly differently. Cami, yes, it is the rate constant. It's just I was sort of asking what the rate constant is, like what is it? But yes, so K is, I like to sort of remind us that it's the quantitative relationship or proportionality between rate and the concentration of reactants. And you might notice that I write conc a lot instead of concentration, just because it takes a really long time to write the extra, like 5 letters, or I'm lazy. I'll let you guys decide which one it is. What do the small n and o mean? So I just randomly picked those letters, the aliens are coming, and we're going to talk about those under orders of reaction because that's what they are. Those things there are the orders of reaction. So I could just as easily as said like X and Y, or little a and little b, it doesn't really matter. So what is order of reaction? So I'm gonna sort of like, instead of asking for a real description, I'm going to put if rate is proportional, so directly proportional, that sign there means proportional. If rate is directly proportional to A, what is the order of reaction in regards to A? That's what I'm going to ask. It's first order. Yes, Logan. Yes, Charlie. Yes, Fatima. Beautiful. It's first. So the orders of reaction, so this X and Y, they talk about what the proportionality between the rate and the concentration is. So for example, if you have a rate that is proportional to the concentration of A squared, the order of the reaction is what? Don't worry, we're going to keep going. Taiwu. Second order. Second, yeah. So if the rate is proportional to the concentration squared, then it's second order. So what I mean by the rate being proportional to the concentration squared is that, let's say you double the concentration. Let's say you had 3 moles per dm squared and you doubled it to 6 moles per dm squared. Then the rate, instead of doubling, would be 2 to the power of 2. So the rate would be quadrupled. So that's what we mean by second order. So again, let's say we have the rate proportional to the concentration of A to the power of 5. What order of reaction is that? Yeah, it's the 5th order. Exactly. Is that making more sense? 0 order? So Charlie, 0 order is when the rate, it does not have any relationship with a given reactant. So that often happens with something like water, where it's sort of there, but it's got in such large amounts that changing its concentration doesn't really do anything to the rate of reaction. That's what 0 order is. Does that exist? Yes, it does. So anytime where you have a reactant that's in excess, which just means that you have so much of it that changing its concentration is really not going to change the way it's interacting with anything. Is that making sense? Can I move on to... Yes. Yay, okay. Excellent. Cool. Activation enthalpy then. We shall go on to... So you guys will have done... Will you be showing how to work it out with a proper question? No, Aisha, because this was, we did orders of reaction in the last web class, which you can watch. Again, you can't ask questions, but you can watch it. So this is sort of like the follow-on. This is like rate equation number 2. So no, but it will get used in the questions. So you might be picking it up more, but you should probably go and watch that web class either after this or I mean, like, you can't ask questions, obviously, because I won't actually be in there. But, you know, the energy needed to start a reaction is Jazel's answer for what is activation enthalpy. Yes, but less sort of like, can we zoom in further? Instead of like looking at it and maybe like a reaction vessel of some kind, can we zoom in and think about the particles? Ooh, so Shahid Chowdhury says minimum amount of energy needed to start a collision between the reactants. So we're almost there. Collisions are taking place, but activation enthalpy is something that happens when a collision takes place. So like we've got, because you can kind of assume if something's a liquid, it's always bumping into everything else, right? What needs to happen when they do bump into things? Yes, Emily Winter, you got it. Yeah, so it's the minimum amount of energy needed that when particles collide, they actually react, because they're colliding all the time, but you need them to have enough like sort of oomph that when they do crash into each other, something actually happens and they don't just bounce off. So I'm going to put that in. So activation enthalpy is the minimum energy required for a collision between particles to cause a reaction. Yes, Leonide. So that's also a good definition of activation enthalpy. So you can be talking about ground state and transition state as well. I was just sort of talking on a thermodynamic perspective rather than looking at it graphically, but you're totally right. Oh, yay, Princess Rositosa. I'm really, really glad that it is helpful so far, even though this is the what we should already know kind of section. I'm going to move on to the things that we shouldn't know yet, or that you might know if you've done it already in class. I hope you've done it already in class. But before we do that, I want you guys to just take a look at your spec points. So the important thing, oh, I'm going to move. How do you move the tiny human? Sorry, my own tiny box with myself in it was covering up the spec points. Yes. So these are your AQA spec points. I will also show you OCR and EdXL, but if you're on AQA, just have a quick glance through. I say this every time, but you should really be keeping an eye on your spec points just throughout your 2 years of A-levels, and like taking them off once you know them, and then having like another column to tick off once you've revised them, and then another column to tick them off when you've revised them the second time, because obviously the first time it's not going to go in. But yes, so moving on. So these are your EdXL spec points. Have a look really, really quick, because I'm not going to stick on them too long. And OCR, here are your spec points for this topic. All right. Cool. So let's get started. So we're going to be talking about rate concentration graphs. And the thing that tends to trip up students in exams is that you have both rate concentration graphs and you have concentration time graphs. So please don't confuse them, because they have different meanings and different analyses. So what we're going to do is look at how we can tell if something is 0 order, first order, or second order. So how the reactant is proportional to the rate. So, I mean, like, somebody take a stab at this one. What do you think? So if we're looking at the rate of reaction, and as our reactant goes up along the bottom, the rate doesn't change, what kind of order of reaction is that? 0 order, yeah, 0. Thank you, Emily, Fatima, Logan, Cami. All of you are totally right. Oh no, what's happening? So this one is 0 order. Cool. So I'm just going to sort of label this no change in rate associated with change in conc. Also, if you can't read my writing, please tell me, because sometimes I can't read my writing. And I want you guys to be able to see what I've said. That is not an N, is it? All right, there you go, an N, cool. So what about if we're looking at the second one here, and we've got sort of like this straight line relationship between our substrate concentration, substrate, reactant concentration and rate. Yeah, everybody's can't read it. Yeah, sorry, Aisha. Okay, let me rewrite that for you. Yes, and then all the people who said first order are totally right. So this is first order. And I'm going to rewrite this sentence because literally it's possibly illegible. So no change in rate. And while I'm writing this slightly less badly, somebody tell me, what could we write about first order? What kind of relationship is that? With change in why is it first order? So Cami says, why is it first order? Jaisal says, an increase in there's an increase in rate, so it's linear. Yes, so it's first order because they're directly proportional. Like, for example, if this was going up by like a factor of 5, this along here would also have been going up by a factor of 5. So it's first order because there's a direct proportionality rather than sort of like a square proportionality or a cubed proportionality. So we call the relationship between concentration and rate and first order reactions in a rate concentration graph a linear relationship. So anything that's directly proportional has a linear relationship. Is that all that seems like it's making sense? Positive correlation. Yes, it is a positive correlation. You don't tend to need to say that in the exam, but you're right, it is positive. It's direct proportionality also. Wicked. Okay, so the last one, I mean, like, take a guess. It's quite logical what the last one is going to be. Have a go. Yeah, second order. Oops, the screen does not like to stay where it is. So this one is second order, and we just call it an upward curve. So a lot of you guys are saying exponential. And we did have an exponential relationship in the last one because in our time rate graphs, there is an exponential relationship in first order, which is why it's so important to recognize what kind of graph this is. Because if this instead was time, it would look like this for first order. It would be an exponential graph. So just be so careful to check. I cannot reiterate enough how important it is for you to check what's on the axes. So yes, there's an upward curve relationship, meaning that as you increase the concentration of the reactant, the rate increases disproportionately, but more, so like squared. So if I write down the proportionality to remind us, but maybe up here. So rate is proportional to x squared. Could it also be third order for a third graph? Yeah, definitely, Logan. It's just that we tend to only study up to second order because mainly you don't really get reactants that are that important to rate. Usually it is sort of goes up to second order. And often it really isn't as simple as this. So like this is useful, but also comes at sort of like it's like minimally useful. Yes, wicked. All right, I'm going to move on because this is sort of like, what is happening here? Yes. So oh goodness. Sorry, I realize I am looking confused. I think it's because I definitely skipped a slide, but the slides look the same. Oh, okay. Yeah, I skipped a slide because they look similar. Apologies. So we're going to do what this slide was supposed to be on this slide. So we in this slide did not look at rate constants. We looked at order of reaction. And for this one, we're going to be looking at rate constants instead of order of reaction. So apologies. Straightforward. Okay, cool. So if the year axis was half time, then the rate. So we did half-lives in the last web class. So if you want to go over that, Leonide, you should watch the last web class. And those are on time concentration graphs, not rate concentration graphs. But we're going to look at rate constants on rate concentration graphs. So for all of these, you can work out the rate constant. If year axis was half time, it would be 0. So I'm just reading Leonide's question. If the year axis was half time, then rate of reaction would be 0. Leonide, you might want to rephrase that because I have no idea what you mean by that. But if you're asking about half-life, then yes, it was the last one. But okay, so we're going to look at how to find the rate constant on rate concentration graphs as opposed to time concentration graphs. So does anyone have any idea for 0 order? So we already know this is 0 order because we did that in the next slide. So, yep, it's 0 order, but where on this graph can we find the rate constant? So if you guys remember that the rate constant is the relationship between the rate and the concentration, that might help you. What sort of part of a graph tells you about the relationship of things? The gradient, yeah. So because this is 0 order, the gradient doesn't really tell us anything, but you guys are right in the respect of the first order reaction, because certainly the gradient of this line is going to tell us the rate constant. So for first order reactions in rate concentration graphs, the gradient is the rate constant. And this is one of the reasons we do rate concentration graphs instead of time concentration graphs, because it's way easier to find the rate constant. For this one, it's actually just the y-intercept. Cool, so k equals the rate. So k equals the rate constant deca, not, or deca. But yes, so for 0 order reactions, the y-intercept is our rate constant. And for first order, the gradient is the rate constant. So for second order, this is where everything gets kind of complicated. I'm going to give you guys like 20 seconds to see if somebody already knows. Does somebody already know how you work out the rate constant for second order reactions on rate concentration graphs? So it's not a tangent. So we're again thinking about concentration time graphs. It's not a tangent. Not a tangent. So this is that is definitely for time concentration graphs, which is so important for you guys to be like remembering what method is for time concentration and what method is for rate concentration. What can we do? Yeah, so Shahid Chowdhury says dy by dx, which is kind of right. So we're still talking, gradient is still important. So what we're going to do with this graph, well, what you guys are going to do, because we're not actually going to like do it on here, is you plot a second graph. You plot a second graph of rate against x squared instead of rate against x. Does that make sense? Because it's second order. So the relationship should be between rate and x squared instead, because if we remember that for second order, rate is proportional to x squared. So you plot a second graph against x squared, and then it's the gradient of that gives you the rate constant. Does that make sense? Is the second graph the tangent one? I mean, if the way you don't get it, can I draw a rough sketch? Does it give a, so, okay, I wish I had a blank page. Okay, I'm gonna use this. So let's say I'm gonna draw like a table, and let's have concentration of like what? Let's just call it A. Sorry, yes, I can draw a rough sketch, is why I'm making this table, Jaisal. And then we're gonna put rate over here. And if it's second order, let's say that we have, when it times is by 2, so let's say at, if it goes up, if it times is by 2, then a rate is going to be squared. And if we're timesing it by, so let me get a calculator. So that one should be, so if I've timesed that now by 3, then I should be timesing 3 by 3 squared. So that should be 27. And if that's 8, then it should be 3 times 4 squared. It's 48. All right. So if I had a graph of this, it would look something like this, right? And then if I, instead of plotting there against, would I square the values? Yes, that's exactly what I mean. So here instead, I'm going to put a squared. So a squared would be 4, and then it would be 16, and then it would be 36, and then it would be 64. So the, isn't 4 squared 16? Yes. So sorry, I was working out what the rate would be by doing, for rate, I was doing rate is equal to the concentration of A squared. So is proportional to, sorry, not equal to. So I sort of randomly selected 3. And then when I doubled that, I did that times 4 squared isn't. What about K? So yes, so what we're doing here is, instead of plotting A against rate, I'm going to plot the rate against A squared, right? Why is K not included? Because we're getting there, Aisha. K is what you work out from the gradient, instead of how you, it's the result of this method. So if I actually like literally plot, so I should have 3 times 2 squared. Sorry, that one should be 12. Not that. All right. So if I have a squared on the bottom, that is this, when you have a sequence like 4, 16, 36, 64, that's a squared sequence. And then if you have something like rate going up also in a squared sequence, you get sort of like a linear graph instead of a curved graph. And then you can just work out the gradient of that to get K. Is that making any more sense, or have I confused you more? Do let me know. Any feedback? So I need some emoji feedback, people, because I can't tell if you guys are getting what I'm talking about. Will that come up in the, so you're just going to need to know how to do it. I highly doubt you'll be asked to redraw the graph. What's the bottom axis? It's a squared. Okay, I'm going to put it back on the other one because it will make sense with the other diagram there. I just sort of wanted more space. So instead of, if you want to work out the order of the reaction, if you want to work out the rate constant in a second order graph that is a rate concentration graph, to get rid of the curve, instead of plotting rate against the concentration of the reactant, you plot the rate against the concentration of the reactant squared. Does that make sense? How did I calculate the rate? That's not really important because I was just coming up with values like that, those kind of values would be in an exam question. So I was coming up with them on the fly. You won't have to do that. So the point, you don't have to, so you won't be asked to draw it on the same graph. When they meet, that's not important, it's the gradient. So once you've plotted rate against the concentration of the reactant squared, the gradient of that line is K. Does that make sense? Yes? So you might be thinking of, I think what you're thinking of is when you work out the tangent in a time concentration graph, not a rate concentration graph. So I think that might be where you're getting a bit confused, Taiwo. So like, that's why I keep reiterating like over and over again that the rate concentration graphs and the time concentration graphs, they look so similar, but they have, you work things out so differently on them. So what I suggest you do is look at your notes for time concentration graphs and look at them for rate and come up with some system of memorizing which one is which methods are for which. But I'm going to move on. And then we're gonna, I've already kind of asked you guys how you're feeling, but like sort of overall for that section. So that was this one, how to work out the order of reaction, how to work out the rate constant. Are we all okay with that? Can I move on to the exam questions? No, so you, the calculation, I was just, you calculating rate numbers. So Aisha, I literally just like picked a random first rate, and then I times it by 2 squared because I times the first concentration by 2, and because it's second order, whatever the concentration times is by, you square it because it's second order. So Aisha's confused. Can you tell me what exactly you're confused about? When you saw me with a calculator, you don't need to be doing that. That was just me coming up with an example. So if you've got a sad face, the important thing for you to do is to tell me what is confusing. What is confusing? Because if you don't tell me what's confusing, I can't go back over it. Confused with the last part. So that was this part. Okay, I'm going to run through it really quick because lots of people are happy. So what I'm going to do is just go through super fast. So by last part, do you mean just the second order bit, the second order graph? Okay, the third graph. All right. So in this graph, what we have is a second order relationship between rate and reactant X. And you can't find the rate constant K. So rate constant being this. So in our rate equation, if we have rate equals K and then reactant X squared, because it's second order, so this would be the rate equation for here, and we want to find X, then instead of using this graph, we rewrite the graph. We find our values for X and then we square them all. And then we replot it for X squared. And then from that, so pretend this line is no longer there because I've redrawn this graph. And now I have a straight line, even though that's the worst straight line I've drawn possibly. And then you work out the gradient of that, and that will give you K. Does that make sense? Yes. So you find the gradient of the line X squared instead of, so like literally if you have a list of X values that are like 2 and 4 and 6 and 8, you'd square them all and then replot it so that you would have 4 and 16 and 36 and 64. Does that make sense? Why can't you pick a random point, substitute and rearrange for? Because that would suggest that it has changed to now be used. Can you guys still hear me? Sorry, I just got like a little alert that says you can't hear me anymore, but nobody's saying they can't hear me, so I'm just going to leave it. But yes, so why can't you pick a random point? Because that won't, because then the point changes. So if you if you think about y equals mx plus c, k is essentially what we want it to be, is the gradient, right? So because it's squared, y equals mx plus c no longer applies. It's a squared graph. So you have to square it so that you can use a straight line to find the gradient instead. I hope that makes sense. I'm going to move on to the exam questions because they will help with the understanding of this. Thank you, everybody that responded to my question as to whether you could hear me or not. Okay, so if after this exam question you're still confused, do let me know. I think there's quite a few exam questions, so it should really like shove stuff in a little bit more. All right, so we've got the rate of reaction was measured at several different concentrations of A in the presence of a large excess of compound B and a constant amount of catalyst X. To find the order of the reaction with respect to A, the results are shown below. Explain how the graph confirms that the reaction is first order with respect to A. So the first thing that we do in all exam questions for rate is we check what are on the axes of the graph, right? Because I keep saying sort of over and over again that the rate concentration graphs are different from the time concentration graphs. So even though I've obviously selected these questions specifically to be rate, we're still going to check it. So we've got concentration on the bottom as we usually have, and we have rate here, so it's rate concentration. So the question is, explain how the graph confirms that the reaction is first order. And if you guys remember back to the slide, we used a word to describe the relationship. So does anybody remember what that word was? How do we describe this line? Yeah, lovely, Molly. Directly proportional, proportional. Yes, so everyone's saying directly proportional. You also want to chuck in a linear, just in case. But yes, it's a directly proportional relationship. So we want to say rate increases linearly with respect to concentration. And you can also add that that means there's a direct proportionality, but it's asking you about the graph specifically. So you want to describe what you can see on the graph. Yeah. Lovely. Okay, so that was nice one. Lots of people. Is that a word? Is what a word? Aisha says directly proportional, linearly. Yes, linearly is a word. It's a bit of a mouthful, but yes, linearly. Cool. So the next question is sort of forcing us to think about the difference between concentration graphs. So the first one says, can you guys see the whole question? You can. The first graph says, which could be a graph for the concentration of a reaction on the vertical axis against time? I'm going to underline this, against time, not rate, against time for a zero order reaction. Any ideas? Not D for a zero order reaction. We have one, yeah. So both Naisha and Leonide have got it. It's B. So if we had, so it's saying on the vertical axis is, what is it? What does it say the vertical axis? Concentration of reaction of the vertical axis. Yeah. YB. So if we notice, sorry, I'm going to move my tiny head again. Concentration graph. So this is, so it really states the concentration of the reaction on the vertical axis, and then time on the bottom. So if Y, B, and not C, so if it's zero order, and remember this is concentration against time, not concentration against rate, if as the reactant goes down over time, there's no fluctuation in the relationship between the sort of concentration of the reactant over time, let's say the concentration of the reactant did affect the rate of reaction, then you would see sort of like a bend in the graph, right? Because the having less and less reactant would slow the reaction down over time, because it does affect the rate of reaction. But because there's no effect on the rate of reaction, the gradient, i.e. the rate, stays the same. Does that make sense? Yeah, because concentration time graphs, in concentration time graphs, the rate is the gradient. And as you can see, the gradient doesn't change as the concentration changes. You don't have to apologize if you don't get it. It's my job to help you get it. So are we sort of aware that if you take the gradient of a concentration time graph, the gradient will be the rate, right? Because gradient just means how does this thing change over time? And rate is how something changes over time. So this gradient is our rate. And as you can see, the rate is the same. That's what a linear graph is. A linear graph is when the gradient is the same along the line. So if the rate / gradient does not change as our concentration of reactant goes down, then it must be zero order. But the rate for D doesn't change. Yes, that's true, Fatima, but because it said that the concentration of the reactant is on the vertical axis over time, there's just not a reaction where it's going to be going up over time, right? That doesn't quite make sense. Does that make sense? Which bit makes sense, Princess? What's confusing? Do you first do you understand that the gradient in a concentration time graph is the rate? Does that bit make sense so far? I'm talking directly to you, Aisha. No, so it doesn't make sense that the rate would be the same as the gradient. So there's a statement I'm going to have to get you to sort of like try to internalize. That gradient is just asking the question, how does this change over time, right? So if you work out gradient, it's always rise over run. So you're always doing like that bit divided by that bit. And all that tells you is how it's changing. So if you can sort of, this is more of a maths thing than a chemistry thing, but if you can kind of accept that as gradient, if gradient is change, gradient just means how does the concentration of X change over time? And that is the rate of reaction, right? Because as the concentration of the reactant changes, that's the reaction progressing. So the gradient has to be the rate. Gradient is always the rate in a concentration time graph. And the gradient doesn't change because it's linear. So that's another maths thing. If you have a linear graph, it means that the gradient is constant, which also means that the rate is constant. Does that make sense? And I've got a lot of people saying, why is it not D? So D is, yes, D is linear, but if you think about it, if we've got X on the vertical axis, so it specifies it's got to be on the vertical axis, there is X is the reactant, not the product. So it can't go up over time. So this graph just doesn't make any sense. Yes, rated mega. Thank you, great. Thank you, rated mega. This can be like a group effort teaching session. Is it making sense? Is why it's not, is everyone okay? Because I have a sense that there's people getting quite confused. Aisha, so rate decreases as it's negative. So rate does not decrease because rate isn't either of the axes, Aisha. Rate is the gradient. So it doesn't matter whether you were to look at this point on the line or this point on the line or this point on the line, the gradient is exactly the same. And gradient is the rate, which means that gradient does not change when the concentration of the reactant changes. Does that make sense? Yes. So would it be a negative number? Yes, the gradient would be a negative. But that doesn't matter rate-wise. You would just sort of take the size of the number rather than the fact that it's negative. Does that make sense? So this is sort of like one of those things where it's a really good idea to just go open a GCSE maths textbook on the sort of y equals mx plus c chapter, the straight line graph chapter, because you do really need to know that for your A-level chemistry. So revising it is a good idea. So we're getting people saying that they're getting it. I'm really, really happy. Am I good to move on to B? Can I see a sort of sprinkling of emojis? I am really enjoying having my cup of tea because like talking for like an hour is so sort of not good on the throat. Yeah, go on. I'm good to move on. I'm getting some thumbs up. I'm going to give it another 5 seconds and then I'm going to move on to B. Oh, yay. Okay. All right. Cool. We're going to move on. Scribbling, scribbling, scribbling. Okay. So B, which could be the graph of a rate of reaction on the vertical axis against the concentration for a first order reaction. So this is something you guys should be familiar from one of the other slides because it's rate against concentration, which is what we've been doing. Yeah, all of you are right, it's D. It's D because as you remember, for when we have concentration on the bottom and rate on this axis, then a linear relationship must be first order. Yes, beautiful. So I'm gonna move straight on then to C, which says which could be the graph of rate of reaction on the vertical axis against the square of a concentration for a second order reaction. What if it's against time? So Aisha, I really think you should watch the web class from last Thursday because that covers all of that. So last Thursday we covered time concentration graphs, and this time we're covering rate concentration. Apparently my words don't work anymore. Rate concentration graphs is today. So if you watch the other one after this, you should have good comparisons. I'm getting a lot of A. Do you guys remember? Do you remember what happens when you plot against the square? So when you've got x squared on the bottom, why do we do that? Why? Somebody tell me, why do we square it when it's a concentration rate graph? Anyone? What's the point of squaring it? What does it look like when you don't square it? Yeah, it makes it linear. Yeah, you can't find a constant gradient if it's not linear, because a curve literally means that you have a changing gradient as you go. So yes, so you want to make it linear so that you can calculate K, and we only really have one option for a graph, which is so I know lots of you already said it, but tell me again. And anyone that might have changed their mind now that they remember that the whole point of making a squared graph was to make it linear. So it's not A, guys, because this would be A would be rate against the concentration for a second order reaction. You guys are totally right about that. But that's not what the question says. The question says which would be rate against the square of the concentration. And if you remember from the other one, if you square it, you get a linear graph. Is that making sense? So it's going to be D again. Yeah, I hope that makes sense, lovely people, because I'm going to move us on because we have spent an awfully long time on this. And I'm saying we spent a lot of time, but I don't want you guys to be like, oh no, I wasn't getting it, because this is like a really difficult topic. So we're going to move on to the Arrhenius equation, which is sort of equally tricky. I'm so sorry, but this is another one where it's super useful to remember your GCSE maths. If you are remembering that you do not remember your GCSE maths, this is the time to revise it. Not like right this second, but like this time of year, you really need to be doing that. Can I explain the graph for C? Is that AQA? All of this comes up in all of them. Can I explain the graph for C? So I'm going to do that at the end in the questions, because we really do need to move on, because it's almost 7:30. So it means I've been going on for an hour and we're not like, this isn't even halfway through. We may not actually be able to finish this. So let's move on. And then I will go back to see when we do the questions at the end, but do remind me or I will forget. Okay, so we're going to talk about how rate is affected by temperature. And I think the thing that's really, really important to remember about temperature is that when you zoom into particles, temperature is basically a measure of how strongly particles are vibrating and moving around. So it's kinetic energy, but really, really tiny. So when you increase temperature, you also increase collisions. And what were we talking about with collisions earlier on? What was important about collisions? Yeah, so we've got Jaisal mentioning EA, so our activation enthalpy. So if you have more collisions, you have a higher probability that one of them is going to cause a reaction, right? So when you increase temperature, you sort of increase the probability of something happening. So I'm going to write that down. I'm going to put under this affects rate, we're going to put the first point is that an increased number of collisions is equal to an increased chance of reaction, which gives you the likelihood of an increased rate. And I've got somebody chucking in already the equation, but we're starting slow, Ali. So give me a second, and your magical knowledge of equations and ability to actually write them down in words, which is kind of tricky. Okay, so that's our first thing. We've increased the number of collisions. We also, so temperature is tells us about the energy those particles have, right? Not damn, it will be useful in a second, Dan. So if these particles have more energy, what do they have more of a chance of when they're colliding? So not only do they have an increased chance of colliding, what else do they have more of a chance of? Anybody? So when they actually collide, if they have more energy, yeah. So Ali says more successful collisions with activation enthalpy. Why do less molecules have the? They don't. Yes, Cami, they have and Charlie. Yeah, more chances of a successful collision rather than a collision. Rated Mega, I don't understand your question. Could you rephrase it? So yes, I'm going to write that down. So if we have an increased number of particles with energy above, random line, activation enthalpy, and I'm writing EA instead of activation enthalpy, but it means activation enthalpy, then we have which means that we have an increased chance of reaction, which means we have an increased rate. So we're asking about the area under the graph. What does the high P? Okay, so let's have a look at the graph. So the graph is number of particles with energy, and the bottom is the activation enthalpy. So this is an, I think that maybe you're thinking that it's a temperature against number of particles or temperature against activation enthalpy, but it's not. We've got temperature 1, temperature 2. So what we're really saying is that temperature 2 is greater. Ooh, there's a spider on my laptop. Temperature 2 is a greater temperature, which means that instead of sort of like, it's not about the size of the peak, it's about the area under the graph. Did Ali already say that? Yeah, cool. So you understood the question before I did. Thank you, Ali. You're very useful today. You're doing part of my job for me. I appreciate it. Yes. So even though the peak is larger, what we're talking about with the number of things that are likely to react is the area under the graph. You can't really tell with wiggly ones from just the size of the peak. Cool. So I'm going to move on. So far we know that temperature increases the likelihood of, increases the rate of reaction because it increases the collisions and it increases the number of particles that are with an energy above activation enthalpy. So this is all described by the Arrhenius equation. And that links our activation enthalpy with the rate constant. So this is, when we're talking about our exponential graphs, you know, the ones that look like this, that's a really bad exponential graph. The ones that kind of curve upwards, they are, that sort of thing is E. That's what we mean by E. That sort of describes that kind of curved relationship, right? So all I'm going to do on this page is talk about what each of these terms mean. So you guys should all know what K is. So tell me what K. What is K? Rate constant. Yes, thank you. Whoopsie. So we have K is the rate constant. Cool. So I'm not going to ask you what A is because you don't know yet, but I'm going to ask you what EA is. What is EA? Anybody? Activation enthalpy or energy. Take your pick. So we've got activation energy, and I'm going to give you the units for that. And just please remember how important units are. So it's in joules per mole, not kilojoules per mole. So T is probably reasonably obvious as well. What is T? Yeah, you're right, Mega. I'm just going to call you Mega, rated Mega, because apparently that's what my brain does. Yeah, everyone is saying temperature. So cool. Yeah, temperature in Kelvin, because we never use degrees in chemistry, really, unless you're doing an experiment. Cheeky Nando's fam. Don't talk about Nando's or you'll make me hungry because I have not had dinner yet. So that's cruel, Adam. That's what that is. Right. So temperature. Everyone got it. Cool. What is R? So this one is trickier, but you will have seen it before at some point. Does anyone know what R is? Gas constant. Wicked. Yeah. How long has this been on? Since 6:30. It's going quite slowly, so I'm probably going to have to chop off an entire section, people, I'm afraid, because it's taken a lot longer. Then hopefully I'll be able to time the future ones a little bit better because, you know, these are new web classes. But yes, I really appreciate you guys' attendance and feedback and everything. So the gas constant will be given in your data sheet, so you don't need to remember it, but I'm going to put it, and it's also usually in joules per Kelvin per mole. So all you have to do is make sure that your units are matching the gas constant that's given in your data sheet, and you'll be fine. Ah, all right. No, do part two. The biology teacher is doing the same. Okay. I'm going to do my best to squeeze it in. I'm going to do my very, very best to squeeze it in, people. Just concentrate really hard so that you can understand things like really amazingly fast. I don't know if that's a thing, but I'm going to try. I promise. Okay, so we've got all of these. A is a weird one. Essentially, we call it a pre-exponential factor. And all that means is because E is the exponent, is the exponential, and it sits in front of E, it's pre-exponential. So that really doesn't mean anything. It's just a constant. So it's a pre-exponential, and apparently my brain stopped being able to spell, exponential factor. And all we really need to know for A level is that it's related to the frequency of collisions. So that's all you need to know. And as it's a constant, we do not have any units for it. Yeah. Yes, Aisha, E is something like that. I've got a calculator in front of me. You know, it's been a long time since I actually tried to look at what E is, but my thing doesn't like it. Okay, so yes, Arrhenius constant. It's just a constant. Okay. What is the units for the rate constant? So if you want to know that, then you have to go back to the other web class, because that is what we did in that. There's no single unit for the rate constant. It depends on the order of the reaction. So you have to work out each different order of reaction, and that's in the last one. Is A on the calculator? It's not a number you should know. You will be given it. It's not a number you should know. It's not a calculator either. It's not like one of those sort of regularly used constants. Cool. So we usually use anything with the exponent, so E, we use in its logarithmic form. And the sort of version of the logarithmic form for E is ln. So if you, I'm actually going to like hold up my calculation. I don't know if you can see it properly, but ln is here. It's that one there. So ln just means log to the base E. So if you're doing maths, you should know that. If you're not doing maths, sorry, this is harder for you. So what we're going to do is take logs of both sides of this equation. And again, if you haven't done maths, this is going to be really confusing and you're just going to have to memorize it. If you are doing maths, then it should be less confusing and you don't have to memorize it. You can just do it on the fly if you're confident that your maths is good enough. So we're going to take logs of the k, which will just look like ln k, which is nice. And then when you take logs of anything that is to the power of the exponent, then the exponent just disappears because log ln is basically the opposite of the exponent. So we're just going to write minus EA over R. And instead of putting over RT, we're going to make things easier for a reason you'll see in a second and put it times 1 over T, which is exactly the same, right? Yes, Ali, that's what we're about to do. Help when we're not there yet. Don't help before I've actually got in there. That's sort of like gets people reading the comments instead of watching the thing. So we're taking it slowly, well, at least as slowly as we can with limited time. So the last bit is just the A, and the A is not within the exponent, so we just keep it as ln A like we did ln K. So what we have here is essentially y equals mx plus c, as Ali said, because Ali is a smart bean. So I put it in this form because we want to be able to work out sort of A and EA over R by doing sort of things on the graph. So if we look at this form, the ln K is essentially our y, right? The EA over R is essentially our M. And what is the M in y equals mx plus c? Anyone? What does the M represent in y equals mx plus c? Gradient. Yes, thank you, Logan. Thank you, Tyro. Yeah, so that means that when you have a graph of 1 over t against ln k, the gradient is minus EA over R, which means that you can work out the activation enthalpy from the graph. So that also means that x is 1 over t, which is right because we can see it here on the x-axis, and we can see that ln k is on the y-axis. And then ln A is our plus C. And what does plus C represent in y equals mx plus C? The y-intercept, yeah. So here, our ln A is essentially about 15, right? So if you're given a graph, you can work out ln A and you can work out your activation enthalpy. You just need to remember your log laws. You can check out our videos on logs and the natural logarithm as well. If you aren't doing A-level maths and this is hella confusing, you might just need to learn that bit. So did that all make sense? So the opposite, Emily, the opposite of log is the exponent. So if you want to unlog something, you do the exponent to the power of that, to the power of ln that thing. Everyone's looking happy. 2, yeah, we're getting it. We've got some 2s, but that's okay because we can still do an exam question with a sort of like it's all right kind of deal. Do you need to remember the rearranged version? Yes, the rearranged version is super important for analyzing graphs. So that means we're going to move on to the exam question, which hopefully is not going to be too terrible. So what we should have is this pop up. You guys can all see it. Is EA always positive? Activation enthalpy. It should be. I can't think of a reason why it wouldn't be. So I'm going to go with yes. We're going to get on the question though. The reaction in part B is repeated at 2 different temperatures, keeping the initial volumes and concentrations of the solution constant. Calculate, without drawing a graph, the activation energy of a reaction, remembering to give a sign and units with your answer. So first of all, if we're trying to work out activation energy, yes, Emily, that's why I was sort of like, I can't think of a reason why it wouldn't be. It should be positive because it's endothermic. Chemistry is weird though. So sometimes there are weird situations in which it's not, but let's just assume you guys don't need to know any of those situations. So people, what do we need? What is if we're thinking about it like a graph, what part of the graph would we be looking at to get the activation enthalpy? So we're not actually going to rearrange. What part of the graph when we were looking at the last slide is the activation enthalpy? Yeah, the gradient. Cool. So I'm going to put that in. I'm just going to write gradient is equal to minus activation enthalpy over R, because that is this bit in our lovely y equals mx plus c version that they've very kindly given to you. So can anybody remember what is that equation we use for gradient? Not the rise over run one, the sort of more detailed one. Not dy by dx, but yes, that is one of them. Anyone? The equation for gradient for a straight line graph? Change in y over change in x, yeah. So what we do is, do you guys remember seeing y2 minus y1 over x2 minus x1? That for me? Yeah, I'm getting some of that popping in. Thank you, Jaisal. Yeah, so that's either change in y over change in x or, yeah. So what I'm going to do is randomly assign these two temperature states, so the 293 Kelvin and the 303, 1 and 2, so that we can use that equation. Cool. So what we're doing is, if you guys remember that this bit is y, so the ln rate is our y coordinate and our x coordinate is 1 over t, right? So can you guys write in the, if we're doing y2 minus 1, x2 minus x1, how is that going to look? What should I be writing down? Keeping in mind that ln rate is y and 1 over t is x. I'm going to give you a little bit of time because that is maybe a long thing to write down. I'm going to write down that that's y and that bit's x. And so it should be on the graph here. So here's our temperature. Here is our ln rate. Cool. So Jazels, I mean, you've done it the other way around, but yes. Is there anything? Then divide. Yeah, so we're getting, so the top one is totally fine. Can someone tell me why is the bottom one dodgy for Jazel? So remember that, I want you guys to remember that the x coordinate is 1 over t, and this is just t. So it needs to be changed into 1 over t. Yeah, so we've got some stuff in there. We're getting sort of like some semi dodginess. So you're right, Naisha, you're like almost there, but it shouldn't be 3.41. It should be 3.41 times 10 to the minus 3. So what we're going to do, I'm going to do over here, I'm going to do 1 over t. So I'm going to do the first 1 over t, which should be 1 over 293, which should be 3.41 times 10 to the minus 3. I'm going to do the second 1 over t, which should be 1 over 303, which should be 3.3 times 10 to the minus 3. So that means we can shove this, now that all of our t's are correct, we can shove this straight into the gradient formula. So I'm going to sort of make that a bit smaller. I'm going to run out of space. Okay. So gradient should equal, so I've assigned this 1 and 2, so I'm going to do it minus 3 minus 3.69. So most people got about that far, so well done. We just forgot to do 1 over t, and then we have 3.3 times 10 to the minus 3 minus 3.41 times 10 to the minus 3. Is that all making sense? Is everyone following? Do I need to go back? Are we okay? Yes? We're all right. Gonna give it 10 more seconds and then move on. Yeah, we're getting it. Yeah, it makes sense. Wicked. So when you shove that in a calculator, it should be minus 6272.7. So right now we have this as our gradient. So, so far, where am I going? Right. So far, we know that our gradient, that's a 4, is EA over R. And we now know that EA over R is minus 6272. Oops, 6272.7. So to get just EA, we need to times by R, which they have kindly given us as 8.31. And we can leave, so I'm going to do a quick check of the units. It's kelvins, it's joules, it's moles, so everything is fine. Yes, thank you, Aisha. So we're timesing it by 8.31. And so we should have in the end, and we should have 52126. And I was going to write down my units, but you guys are going to tell me the units. What are the units of activation enthalpy? Does anyone remember? Yes, Logan, wicked. So Aisha, it should be positive because essentially we've got minus activation enthalpy equals a minus number. So the two minuses cancel. Yeah, joules, cool, joules per mole. Yes, so just be careful, Logan. It's not joules per Kelvin per mole, just joules per mole. Yay, okay. Oh, we made it to the end of that exam question. All right, so because you guys really desperately want to do rate determining step, even though it's 10 to 8, I'm gonna like zoom through it. What about the negative sign? So just real quick, keep in mind that we had a negative number here and a negative number here, so they cancelled out because it was minus EA. Cool. Yes, I don't know what that acronym means. Have I gotten old? I don't know what that means. Oh no. Okay. Rate determining step. We are so close, people. We're in the last section, and I believe this has only a few slides, so I think we're going to be okay. So because lots of reactions have like a few steps, not just one step, the order of the reaction gives us clues about which step is the bit that determines the rate, right? So like, let's say you have two steps in a reaction and one's really, really fast and one's really, really slow. The fast one does not matter in terms of rate because the slow one is the thing that takes up all of the time. So the rate determining step is basically like hinting at how the reaction works. And just remember that you cannot have a negative VA because it's endothermic. Energy has to be put in to break bonds. You are totally right, Emily. You have to put in energy to break bonds, but you may have reactions where you sort of don't have, that you might be starting from sort of ions. I have to think about that. But yes, Emily, you are totally right. Yes, so rate determining step is sort of about starting to think about reaction mechanism. So I've got an example here. We've got this sort of substitution reaction between bromine and hydroxide, and essentially it's just swapping out. And we've got this rate equation where we have a rate equation, and the rate equation does not have an OH, but OH is not there, which means that essentially OH is there, but it's got a zero order. So it disappears because anything to the power of 0 is 1. So it disappears. So we've got to assume that OH must not be involved in the rate determining step. And you'll see rate determining step as RDS lots. So what reagent must be involved in the rate determining step? What's the why? What do you mean why, Leonide? And Charles, yeah, you are right. Yeah, so you go. So Jazel, OH is not in the rate determining step. Why is it not involved? So if you work out the rate equation experimentally and you find that the rate does not change no matter what concentration of OH has, that means it's zero order, right? Which means that we don't put it in the rate equation, which means that it can't be in the rate determining step because it doesn't determine the rate at all. Will I be doing a live on mechanisms? Yes, but probably a lot further on in the year because it's right at the end of the syllabus for most people. So yes, so because the only thing in the rate equation is the CH3 3CBr, that means that, CH3 CBr must be part of the RDS. So the rate determining step in A-level is essentially looking at what is zero order and can't be in the rate determining step, and what has an order of reaction that's 1 or above, and that's got to be in the rate determining step. So if we write down a little note and say that when we have, oops, an order above 1, it could be in the RDS. And if we have an order that is equal to 0, it cannot be in the RDS. So that means that when we break this reaction up into 2 steps, so we sort of like think, okay, so for this reaction to happen, the bromine must be removed. So we're going to break that down into what if it's first order, then it can be in the rate determining step. So this means that this step, this has to be the slow step, because it's the step that involves only this, and that's in our rate equation. This step has to be the fast step, because it's the step that's including the thing that's not in the rate equation. And I wouldn't worry too much about being able to come up with steps yourself. You just need to be able to say, this one's in the rate equation, so it's a slow step. This one is not in the rate equation, so it must be in the fast step. So we're going to go straight ahead and do some exam questions. So let's have a look at this process for creating N2. So we've got, it's sort of giving us a lot of the steps already. We know that we've got 2 hydrogens, 2 NOs, and then an N2 and an H2O as our products. So it's telling us that the first sort of step is the fast one. And by the second step, we've only got N2O and H2O, but we want N2. So does somebody want to take a stab at what is this last step here? What is step 3? If we're trying to get to the end of this reaction, so we've got a reagent here. What is our last? Does anyone have any ideas about what the last reaction is going to be? So it's not going to involve N2. It won't involve N2O2 because that's already been used, right? That's been used in step 2. So we want to be using the reactants from here. What do we need? So we've got N2O plus O2. So that's not reasonable, Logan, but we've not got an O2 anywhere else. But we've got lots of sort of agreement that N2O must be involved, and you're totally right, because we know we need that somehow. What's important about the moles? How many moles of water do we have so far? Anyone? How many moles of water have we made in the first 2 steps? 1, yeah. And how many moles should have been made? Yeah. So we should have had 2. So that means that we must put another H2O at the end. So we need to have created a H2O. And it's the same thing. So how many moles of H2 have we used so far in the reaction? 1. Yeah, thank you, Naisha. Thank you, Fatima. We've only used 1, and there's 2. So we know we need to shove in another H2 as our reactant. And there's 1 product that we haven't made so far, right? The actual product of the reaction, the thing that we're looking for. So that's got to be here as well. So essentially, when you get an RDS, a rate determining step question like this, and it's asking you to come up with a step, the most important thing is to A, have the product that the reaction is for, and B, have used up any reactants that we've got too many moles of or too little moles of. Is that making sense? Does how we got step 3 make sense? Can I see some emoji feedback? Oh, sorry, that was supposed to be an N. Thank you, Fatima. H2. Oh, no, that was supposed to be H2. How did I know I had to use N2O? Because it's a product in step 2, but it's not a product of the reaction, so it has to get used up. So hello world is confused. If you're confused, you should tell me what is confusing, or I will not know how to explain it to you. So I will actually go through each thing that I put in. So the NO2 comes from here. It's not in the reactants up here. It's not in the products. So we have to use it up. So I put that there first. We have then added a H2. And that one was chosen because we have 2 moles of H2 here. And in step 1 and 2, only 1 mole is used. So I shoved that in there. Then next we have N2. And I got that because we have a product here that's N2, and N2 is not made anywhere else. So we have to have it as a product in step 3. And H2O is here because we know we make 2 moles. And in step 2, you only make 1 mole. So we had to add that on. So I hope that is all making sense. Hello world, is that less confusing? Aisha's got it. Yes, I'm glad. Got 5 seconds to say it's still confusing. Nope. Okay. All right. So the next question is, explain why this mechanism is consistent with the rate equation. Rate is equal to KH2, which is 1 order, and NO, which is 2 order. How did I know H2 concentration was 1 order? This first order. How did I just shove that in there? How did I know it was first order? Anyone? Because there's no power. Yeah, so Aisha, not because of 2 Aishas both answering the same question. Aisha A, it's not the number of moles, it's because the order of reaction is always the power, and anything that doesn't have a power is to the power of 1. Yeah, because it has no number power, so yeah. So it does have an effect. So remember, 0 order means that it doesn't have effect. First order means that there's a linear relationship and there is an effect. So why, so I'm going to let you guys just go ahead. Why is the mechanism consistent with the rate equation? So remember, they've given you fast, slow, fast. So they've told you what the rate determining step is, because the rate determining step is the slow one. So give me, yeah, and if it was 0 order, it wouldn't be in the equation. You're totally right, Aisha. So anyone? So why is it's essentially asking why these are rate determining, right? So why are these in the rate equation? What can we tell from the mechanism? What can we tell from which ones are fast and which ones are slow? What do you mean by step 2 is in the rate equation? Because those are the reactants in the RDS. Yeah. Because they determine the rate of reaction. Yeah, we've got pieces, but we want sort of like, I'm going to put it more concisely, but we've got the pieces in there. So what I'm going to say is that step 1 and 2 give us 2 give us, sorry, I've confused myself with my own, sorry. Step 1 and 2 give us NO2, give us NO and H2, which are used in the rate, determining step. So we needed N2O2 for the slow step, and so that means that we need NO, which makes sense. And we needed H2 because that's in the rate equation, and that's also in step 2. So that's why they're consistent with the rate equation. I don't understand what this question is asking. So the question is asking it's essentially asking how is the rate equation linked to these steps, right? So we've been given the sort of this reaction up the top, broken down into sort of how it happens step by step. And we've been told which are fast and which are slow. And if you remember, the slow step is the one that determines the rate. So anything that is sort of used or needed for the slow step must be in the rate equation. And because H2 is used in the slow step and it's in the rate equation, that makes sense, right? So we're saying we kind of get it. So H2 is used in the slow step and it's in the rate equation, which totally makes sense. And NO is second order even. And we know that does make sense because this step, the use of NO, is essential for creating this other reactant that's also in the slow step. Yes, Fatima, but we needed the NO to create N2O2, and you don't have, so N2O2 is an intermediate. It's not the thing that you put into the reaction vessel. NO makes the N2O2, so that's the only thing that can be in the rate equation. Does that make sense, Fatima? What about the NO? So and Aisha, both Aisha and Fatima, does that make sense? So because NO is the reactant, N2O2 is an intermediate. So the making of the reaction of NO is really important because it makes the thing that's in the slow step, but you can't put N2O2 in there because you only measure reactants to find the rate equation. Aisha, does that make sense now? Yeah? Cool. So no, catalysts aren't in the rate equation because you're purely talking about reactants. If you remember, sort of like a catalyst affects the rate of reaction but doesn't sort of like get properly involved in the reaction mechanics in the way that you require for a rate equation. But when we do sort of more catalytic things, I think I'll probably go into more detail about that. But no, catalysts aren't in the rate equation. I was going to do a second question, but we really don't have time. So I'm going to skip right to the end. But we did manage to do some rate determining step. Do the lives get removed? What do you mean by the lives, Aisha? Lives of what? While you are answering that, I'm going to just recap what we should know. And if you remember at the very beginning, which was a while ago, we were talking about all of the sort of ways that sticking around is a good idea because you might have won our Insta competition, or you might have gotten or you'll get our code for discount. Do the lives, the live streams. No, they don't. They stick around. You can rewatch it and you can watch the one from last week as well, because I don't think you watched that one. No, they stay. They stick around. They all stick around. Okay, so you should be able to analyze rate concentration graphs. And please, 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 if you weren't around for the first one, watch it or read your book about time concentration graphs, because they look the same, but they have different answers, and you need to be able to tell the difference. We looked at the Arrhenius equation and the effect of temperature on rate, and we very quickly looked at rate determining step. And I really, really appreciate all of your patience, actually. Leonide, yes, I will go back to that. Ali, you can rewatch it. I also want to say thank you to Ali and to, was it Maisie, that sort of were like half doing my job and answering some questions in the top. No, it's Emily. Emily Winter, thank you for answering that question about activation enthalpy and the fact that it's endothermic. I really appreciate that. And Ali, thank you for answering those other questions in the comments. You guys are lovely students to be helping other students. So housekeeping, I really have to show you guys what this is going to be. Like, the whole point of me doing these web classes is to show you guys how awesome it is to have a teacher on YouTube to help you out with your subjects. And we're launching sort of like the full thing on the 16th, and there will be more web classes. They'll be happening in more of the week. And some of them will be free, but most of them will not be. So if you would like to sign up, the web classes are in the ultimate package. If you've already got SnapRevise, or if you buy SnapRevise now, you'll upgrade to basic automatically. And because of the discount that you'll get, it's cheaper to do it now and then upgrade when it comes to October the 16th than it is to buy it later. So I would do it now. If you want to watch the next web class from year 13 is no longer on rate. I believe it's equilibrium. So the next one for year 13 should be equilibrium. Will I explain that? So Leonard, I'm going to do that right at the end. The any questions bit is right at the end. So I'm going to go back to graph C. You're welcome, Princess Rositosa. I just have to do these bits first, Leonid, and my voice is slowly disappearing. Oh no. Okay, so yes, the thing I was supposed to be doing on this one is you can set reminders. So go ahead and set the reminder for the next one next week. And here's your code, because you guys are really wicked for staying around until 8:10. So you get a discount for one of our courses, and it's for like the whole 2 years, even though you guys are in year 13, so it's not 2 years anymore. But it's for a whole year, and it's only like, it's less than a top in Topshop or less than a pair of jeans. So I would totally do it. And then if the web classes, you'll have to upgrade on the 16th, but it will be cheaper for sure. Yes, somebody will be announcing it. My colleague should be doing it. I don't know. Oh, colleague, please do the announcement. Is there a bundle discount for 3 subjects? That's something my colleague that should also answer. If they don't, give us a ring. We're sending the winner a private message. Colleague, we can announce it on the actual thing. It doesn't have to be in a private message necessarily, but if that's the way we're doing it today, then that's fine also. Okay. Is that the price for year 12 and 13? Yes, Fatima. So what I'm going to do is, I can't remember, it was graph C for the other part. Yes, Leonide, I'm going back to that one as promised. This one. Okay, and also, no, don't worry. It was just that I wanted to get through the whole thing before, so that if people did get it, they could go, and then if people didn't get it, they can stick around. So it makes more sense that way. So this question was, which could be a graph of rate of reaction on the vertical axis against the square of the concentration of the second order reaction? And the answer was D. And we're sort of wondering why it's D. I think that was the question. So I'm going to put that it's D. So if you remember, if we go back to this graph and we look at rate against concentration, the graph is a curved graph. I think that's what was confusing you, Leonide, before. He meant graph C. I thought he meant question C. Graph C is not a thing. Graph C is just like a random misnomer in there. What was the, so that's not your question? What was the question, Leonide? Is are we still confused? Or have we realized that we get it? Jazel says ARR40, any relationship to Arrhenius? I have absolutely no idea, Jazel. He meant graph C. Oh, okay. Oh, graph C is just in there. It's just there to confuse you. There's no reason for it. It's just a random graph. Nope. It's not related to anything. It's just there. Oh, I totally could have answered that before. Sorry, I thought you meant, can I re-explain question C, not graph C? Thank you, Daniel, for letting me know that. I mean, like, that's what they do. They come up with lots of different graphs, and then they have like one that's like totally out there and a couple that like could be it to throw you off. But yeah, no, graph C is just random. Any other questions, people? And if there are other questions, then I'm only going to be doing them for like another 3 minutes because we've got to finish this at some point. So unless someone says there's a question within the next 10 seconds, I'm going to release you all from this. Anybody? No, I'm not getting any top tips. Great, bon appetit, have a nice evening. Ah, you're welcome. Can I explain LN? Ah, that's a good question. LN, I will do top tips. Okay, what I'm going to say, Aisha, is that LN is not a chemistry topic, and it's kind of like a whole subject in itself. So I kind of am assuming, Aisha, that you're not doing A-level maths. So what I suggest you do is look at the SnapRevise videos for, it's called the natural logarithm, or the exponent, because E is the opposite of ln. Yes, Charlie, I'm going to do that. But yes, you should watch some videos and then do some questions on ln and the exponent. Is it on YouTube, the full video? So I don't think so. I think that check on the actual SnapRevise website, or colleague, if you could please link it, some of the maths content, that would be really good, because I can't look for it right now, of course. But yes, okay, so Charlie Spokes wants top tips for revising this content. So Charlie, I would say that the most important thing for A-level chemistry is to be doing exam questions over and over and over, and having the mark scheme there, and not assuming that because you've said something similar to the mark scheme, you would have got the marks. Be so harsh, because the examiners are harsh. So go through, check your answers. If basically you haven't said exactly what they say in the mark scheme, do it again, and keep doing it until you can like literally spit out the mark scheme on cue. That's the biggest advice I can give. A-level is about answering exam questions the way they want you to. It's not about, I mean, like, I wish it was about having a great conceptual understanding of chemistry, but it's just not what it is. We do that in physics. I was so confused. Yeah, I'm afraid that a lot of chemistry and physics are really confusing without maths. So you might want to, you could even go to your teacher in school, your maths teacher, and be like, I know I'm not doing maths, but can you just like give me some materials? But of course, that's literally what SnapRevise is for. So if you sign up, then we have all of that material. That's what we're for. We sort of are your tutor, but way cheaper. Oh, wicked. SnapRevise has put the list of maths videos that we have on YouTube. They won't be all of them, but those are them there. I'm going to finish off, guys, because as I mentioned before, when someone cruelly reminded me that Nando's exists, I'm super hungry. And we've overrun massively. So I really appreciate you guys coming and having a look. And good luck, and I'll see you next week. You're welcome. I hope it all made sense. I know that was a hard one. Good night. Lovely, lovely people.